Okay, good evening. Today we're going to have our first lecture regarding plasma wave interactions. This is part of a series on 3 lectures in the topic. The first session is basically introductory. On the second session we will deal with the interaction of waves on non-magnetized plasmas, and then to close the series we will look at the interaction of electromagnetic waves with magnetized plasmas. So let's kick off our discussion by establishing some goals for this lecture. So we are going to use a couple of these, and in particular we're going to be using the 2 expressions that involve the rotational operator, which is this one, which, as we recall, that's the Faraday's law of induction. And then we're going to talk about this one, which is, of course, the Ampere's circuital law that relates the current density with a magnetic field. The rotational of the magnetic field, and then as a function of this thing, which is an effective current density. Now, this effective current density has 2 components. One is the familiar conduction current, which is basically the current that Ampere found on his original experiment, because he used direct current. He didn't have an oscillating electric field. With the advent of oscillating current, alternating current, people started observing the appearance of a mysterious current that had mostly to do with the oscillations in the magnetic field. And that is this term right here. Now this term is what we are, from this point on, we're going to call the displacement current. Now the displacement current is not associated with motion of charged particles per se, but rather with the oscillations of electric field with time. So we are going to define the conduction current density as the product of 2 parameters. One is the electric field, and there's this other parameter that I haven't talked about yet, and this parameter is called the conductivity of the medium. Now, these may not look familiar to you, but you would be surprised if I tell you that this equation that we have right here, the one that I'm going to enclose right now in this little rectangle right here, this equation is actually Ohm's law. If you recall, the regular Ohm's law that we all know from high school is just V equals I times R, or the same. We can actually say that in order to make a detailed derivation, but you can right away tell that the current density, well, of course, is closely related to the macroscopic current that we observe on a circuit. Now, what about the voltage? Recall that the electric field is just the gradient of a thing that we call the electrostatic potential. So right away we see that this term right here is equivalent to the voltage in Ohm's law, and the only thing that's left is this conductivity term, and as its name indicates, going back to the total current density, this capital J that I have here, I'm going to write it as a sum of 2 components, the conduction and the displacement. So the displacement is this term right here, and the conduction is this term all the way out here. So these 2 sum each other, and now on this side I just have the result of taking the rotational of a rotational, which is basically the consequence of taking 2, combining the 2 equations. Now, I'm going to have two terms on the right-hand side. The right-hand side has a second derivative of the electric field with time,